Good morning, grade 12 learners. Welcome to the Science Less channel. Right, today we'll be doing a recap program on the topic of trigonometry, particularly for the grade 12s, since you are having your paper 2 exam tomorrow. It's going to be a bit of a lengthy and fun session. I've tried to summarize most of the important things that are going to be tested on your preparatory exam tomorrow, and also doing a background of some of the things, the basics, that one should know. So this will be offered in the form of questions, and I'll go back to do some form of background work that we need for this topic. So if you look at question 1 here, it actually requires us to understand the reduction formulae. So just for me to recap that or go back to that, I'll just draw here my 4 different quadrants. So this is the first quadrant. Remember, what I'm trying to do here is to do the reduction formulae. Now, reduction formulae, as the name says, these are formulae that we use to reduce angles. So if they give you big angles, we use this formulae to write those angles as a small angle. I'll explain to you what that means in a bit now. Now, the other thing that I want us to have in mind is that we are dealing with an angle theta that lies between 0 degrees and 90 degrees. Remember that we have 0 degrees here, we have 90 degrees here, and this makes the first quadrant. So the first quadrant is made up of angles that are from 0 to 90 degrees. And here we have 180 degrees, and this makes the second quadrant. And here at the bottom we have 270 degrees, and actually this now makes the third quadrant. So this is the second quadrant, and this is the third quadrant. And when we get to this point, we have rotated 360 degrees, so it's a resolution, and this makes the last quadrant, which is the fourth quadrant. Now, in the first quadrant, we define this quadrant using angles, as I'm writing them from 0 to 360 degrees. So in the first quadrant, we have an angle theta. Remember, our angle theta is between 0 and 90 degrees. Now, this means that when you see an angle that is between 0 to 90 degrees, say 10 degrees, 5 degrees, 20 degrees, 30 degrees, 45 degrees, 80 degrees, all those angles are acute angles. They are in the first quadrant. So they will be represented by a theta. Now, you should remember or know that all the trigonometric ratios here, our trig ratios are positive, right? So what does that mean? That means that if I were to take the sine of, say, 15 degrees, this will be a positive number. You can press that on a calculator, you'll see it's a positive number. If you were to take maybe the cos of 30, maybe the tangent of, say, 88, they will all give you positive numbers. Now, another way in which one can define the first quadrant using angles is that if you say 90 degrees minus theta, do you see that if I take this 90 here and I subtract a theta, I subtract an angle that is between 0 to 90, I'll get an angle that is less than 90 because I'm taking away a number from 90, which really that number is between 0 and 90. So I should get an angle or a number that is in that quadrant. So what I'm saying is that if you see a trigonometric ratio that has 90 minus theta, it means that it is in the first quadrant. And again, such trigonometric ratios, all of them will be positive. All of those trig ratios will be positive. Now, how do I mean? Well, what I mean is that if I were to have the sine of, let's say, 90 degrees minus a theta, this will be a positive. That's the first thing that I have to observe, that it will be positive. Now, the second thing that we have to note when we have an angle that is of this form is that the name of our trig ratio, will change to its core function, Now, remember that the sine function is a core function of cosine. That's why here these two names, this one is a sine and this one is a cosine. And in short, usually how we write this, we say this is a sine and we write this as a cos. So cos is a core function, of sine. So these two trigonometric ratios are core functions to each other. Now, if we we go back to this example that I was doing, the first thing that we have to note is that this is the first quadrant, and therefore we're going to have a positive answer, or a positive trigonometric ratio. However, this has to change to its core function. In other words, here I have to write cos, and I'm going to write the theta. Then I take this theta and write it there. So let's recap. The first thing that you do when you're dealing with these trig ratios is that you look at your angle. You can see that 90 minus theta is the first quadrant. And in the first quadrant, all our trig ratios are positive. So I know this has to be a positive trig ratio. But the other thing is that because we are dealing with 90 minus theta, the trig function that I have has to change to its core function. And the core function of sine is a cos, as I was explaining here. Then we write that small angle that's here. So it becomes a cos of theta. That's why we call this a reduction formula, because it took a big angle of 90 minus theta and we wrote it as a small angle of cos theta. So that's how you will define it. Now, you can do this with a cos or with other functions. If we go to the second quadrant, you'll notice that if I take the 180 and I subtract the theta from it, I'll get an angle. So here I have 180 degrees minus theta. I'll get an angle that is within the second quadrant. The number that I'm going to get will fall somewhere within this quadrant. For example, if you say 180 minus 15, 180 minus 30, 180 minus, 45, all those angles, they are acute angle, and therefore when you subtract them from 90, they'll give you an angle in the second quadrant. Now, if you see 180 minus theta, it means it is the second quadrant. Now, in the second quadrant, you should remember or know that only sine is positive, right? So this means that if I were to go, remember this was the first quadrant and now I'm on the second quadrant. If I were to have sine of 180 degrees minus theta, the first thing that I have to note is that this will be a positive number that I get here, and I'm going to then write this as it will reduce to sine theta. So I keep the sine the way it is, and then I take the theta there. But the only important thing that comes through is that this becomes positive. Now, in the second quadrant, all other trig ratios are negative. So here we'll then come and say other trig ratios are negative. So what does that mean? That means if I were to have a cos of 180 degrees minus theta, the first thing that I do is to check this angle is in the second quadrant and I'm having a cos here. It then means my answer has to be negative, because in the second quadrant, only sine is positive. Now, following that, we then have to then say this will be a cos. It will remain as a cos of theta. So it reduces to a cos of this small angle. Then that's why we're saying we are reducing this to that. So this becomes a formula for reducing a big angle to a small angle. You can do the same thing with a tangent, let's say of 180 minus theta. This will be a negative tan theta, because this is the second quadrant and we're having a tan, so it has to be negative, and it will reduce to that small angle theta then. Then that's how you'll find the other trig ratios. But there is another way in which one can actually define the second quadrant in terms of trig ratios. Do you see that if I take this 90 here and I add a theta, so I add an acute angle, an angle between 0 and 90, I'll get angles that fall in this quadrant. For example, if you say 15 plus 90, you'll get an angle within this quadrant. If you say 30 plus 90, you'll get an angle that is not bigger than 180. It will fall within this quadrant. So if you see an angle 90 degrees plus theta, this means it's an angle in the second quadrant. It's an angle in the second quadrant. And again, our sign will be positive when you deal with such angles. So you'll still have sign to be positive when you deal with such angles. Then the other trig ratios or trig functions, sometimes we call them, will be negative, right? So let's go through this again. Now, if we say we're having a sine of 90 degrees plus theta, this means that we are, so we're going to start with the angle here. This angle means we're in a second quadrant. So that means here I'm going to have a positive because, you know, in the second quadrant, sine is positive. And so the other thing that I need to add perhaps here is that the name of our trig function changes to its core function. So here the name changes. So I'm just going to say the name changes here because I don't have space. But what I mean by this is that the name of this function, it's a sine function, it will then change to its core function, which is a cos. Remember I said here that sine and cosine, they are core functions. That's why, you know, here this word here, core function, they took this CO and put it here in front of the sine because it's a core function of sine. Do you see that this is a sine and this is a core? So there's a core function of sine. So, and in short, we write them as sine and cos. So if I have a sine, its core function would be a cos. And now this would then mean that I'm going to have a cos of theta because it will reduce down to a cos of theta. And then that's how you'll do that. Now, if I give you something like sine of 90, no, not sine, but I want to say here cos of 90 degrees plus theta, this will then be negative because now if you check this angle here, it's the second quadrant and we are dealing with a cos. A cos is negative in the second quadrant. And so now we are going to have here the sine of theta because this has to change to its core function, right? Cos has to change to its core function. So that's how you'll define angles in the second quadrant. Now, if you then look at the third quadrant, the way in which we'll define angles in the third quadrant is that if I take the theta and I add on it, if I take 180 and I add on it a theta, what I'll have here is that I'll have 180 degrees plus a theta. If you see an angle like this, it defines the third quadrant. Now, in this quadrant, only tangent is positive. And all other trig ratios, others are negative. All the other trig ratios are negative. So what does that mean? So now here we are in the third quadrant. So if I were to have a tan of 180 degrees plus a theta, no, minus, yes, it's a plus theta here because we are in the third quadrant, minus plus theta, this would then mean I'm going to have a positive tan theta. So this will reduce to a tan theta. Now, if we were to then have a sine of 180 degrees plus theta, the first thing that we're going to look at is that we are in the third quadrant, and in the third quadrant, sine is negative. So we're going to have a negative here. And because of that, we're then going to reduce this to a sine of theta. This will reduce to a sine of theta. Now, if you look at a cos of 180 degrees plus theta, again, you'll see that this is the third quadrant and only tan is positive there. So that because we are dealing with a cos, it's going to be negative and it will reduce down to a cos of theta. Now, the other option that we have is that if we take away from 270 theta, if we subtract theta here, we'll get angles that are within this quadrant. So this is to say that if you were to have 270 degrees minus theta, this defines angles in the third quadrant. And with this one's tangent is still positive here. So tan is still positive in this quadrant. And the other thing is that the other trig ratios, others will be negative. And not only that, the other thing that will happen here is that the name changes. The name changes to its core function, right? It changes to core function. The name will change to a core function. So what does that mean? That means that if I were to have a sine of 270 degrees minus theta, you have to realize that this is the third quadrant because I'm defining 270 minus a theta minus an acute angle. So it will give me an angle that is between 180 and 270. You know, I'll get an angle that is between 180 and 270. Now, when it is like this, you will then check to say, now I'm having here a sine. So it means here I'm going to have a negative number. Why? Because of only tan is positive in the third quadrant. And I'm dealing with a sine here. Now, this means now that the name will change to its core function. The name of sine will then change to its core function. And the core function of sine is really the cos of theta. And then it will reduce to the angle theta there, right? Sometimes you can also get a cos. They could give you a cos of 270 minus theta, and then you can work with that. And also it's possible to get a chord, but chord is usually given in grade 10. So in grade 12, if you know it, it's an advantage, but you don't really have to know it. You can still solve the problems without knowing the chord, because you know, if you look at tangent, a tangent, maybe perhaps I could write this here. If you look at the tangent, its core function, it's a core tangent. Its core function, it's a core tangent. Again, you can see that in front of the name tangent, we put a core because they are core functions to each other. So tangent and a chord, they are core functions. So again, if you were to do a tan, it will change to a chord. If you are doing a chord, it will change to a tangent. But don't worry about that, because in grade 12, you don't really have to work with it. Then we go to the fourth quadrant now. If you then go to the fourth quadrant, you would see that I can define angles here by saying 360 minus theta. You'll get angles that are in the fourth quadrant, or when you see that, it means these are angles in the fourth quadrant. Now here, only cosine is positive, then others are negative. Others are negative. Now, this means that if you were to get, let's say, a tangent of 360 degrees minus theta, this will be given by a negative tan theta. Why? Because this is the fourth quadrant, this is a tan, and tan must be negative in the fourth quadrant, and it will reduce down to just tan of the small angle, the theta. Now, if I were to give you a cos of 360 degrees minus theta, this will simply be positive cos theta, because in the fourth quadrant, remember this means fourth quadrant and we're dealing with a cos. In the fourth quadrant, cos is positive and it will only reduce to that. I'm not going to do that of sine. I think it should be obvious to you that it's going to be negative sine theta. Then there is always another way to define angles in this quadrant. We can always say 270 plus theta. Do you see that if I'm adding an angle here, theta, I'll get angles that are in this quadrant. And this would then mean that cosine is still positive in this quadrant. And then the other angles, the other trig ratios are negative. But the other thing that comes here is that the name then changes. Right, the name changes. So this means that if I were to then have now here cos of 270 degrees plus a theta, this will actually give me a no, it can be a negative, it will be a positive here, because we are starting with a cos. So cos is positive in the fourth quadrant. And because remember, 270 plus theta is a fourth quadrant. And the other thing is that because this is cos and it goes with 270 plus theta, it will change to its core function, so that then now it is sine of theta. Remember, the core function of cos is a sine. Now, with all this, we can really use them to then answer questions or change trigonometric ratios that are big to small trigonometric ratios, because, you know, as I was saying, this will be a big angle and this is a small angle. So we are moving from a big to a small angle. But an important observation is that these are the same, you know. So what I'm saying is that if you pick any angle here, let's say you say this is 30, and you also put a 30 here, and you press this on a calculator, you see that we get the same number on both sides. They will be equal. You can test that with your calculator, right? Now let's see how we can use this to solve problems. Say then now we go to question 1. They say here, write down the following as ratio of an acute angle. Do you see that? We are having these trigonometric ratios with big angles, and then they want us to write them as ratios of acute angles, meaning a small angle. You know, that's what I'm saying, that then already they're already telling you that we have to reduce these angles, because, you know, when you write them as an acute angle, it's a small angle, it is reduced. So that means you have to use the reduction formula, right? I hope the language makes sense, and, you know, we are on the same page. Now, if we were to do 1.1, we actually have here in 1.1 the sine of 312 degrees. The first thing that you'll do is that you can rewrite this, you know, as one of the quadrants, as angles in the quadrants. So you have to notice that this angle here is actually in the fourth quadrant, right? 312 is in the fourth quadrant, and in the fourth quadrant we actually define angles as what? 360 degrees minus theta. So we have to subtract some angle here. Now this is where you can use your calculator to say, if we are to say 360 minus 312, we get 48. So it means here, if I subtract 48 degrees, you know, these angles are the same, you know, because when you say 360 degrees minus 48, I get 312, right? Now, look at this. If you look at this, it looks like something that we have done, you know, it looks like something in the fourth quadrant, 360 minus, right? Then we apply our rules of reduction. How do we apply these rules? Well, the first thing that we have to notice that, of course, this we said is the fourth quadrant, and we are dealing with a sign here. It means it's going to be a negative, right? Because, you know, only cos is positive in the fourth quadrant. But the other thing then now is that this here is a sign. It means it will remain as a sine of 48 degrees, right? That will remain as a sine of 48 degrees. Alternatively, one can say that this can also be written as sine of, remember, we can define the fourth quadrant as 270 minus, no, 270 plus, 270 plus. So this would mean that if you say 312 that I started with, and then I subtract the 270, because remember, we're saying we can define this as a 270 as well, I get a 42. So that means here I can say 42 degrees. So what am I saying? I'm saying if I take 270 and I add 42, I'll get this angle here of 312. Now this now can then be reduced to say I'm in the fourth quadrant. So it means, and I'm dealing with a sign here, it means this would be a negative. And it will change to its core function, because now remember, I'm using a 270. Remember, when you use a 270, it will change to its core function. So this will be a cos of 42 degrees. Now I want you to just to test if these things are correct and they're making sense. In your calculator, punch the sine of 312 degrees and see what number you get, and also punch the sine of negative 48 degrees and punch the negative cos of 48 degrees and see what number you get. You should get the same number for all these three. So that's how you'll basically be doing it. Now if we go to 1.2, we are given here the sign of 1, 2, 3. So we're having here the sign of 1, 2, 3. The first thing that you do, the first step would be doing what? Checking what quadrant this is, right? And we can see that this is the second quadrant. I mean, 123 degrees Celsius lies in the second quadrant. And in the second quadrant, we actually can write angles as 180 degrees minus. So this means here, if I say 180 degrees minus 1, 2, 3, I get a 57. So this means here I'll write the 57 degrees. Now if you say 180 minus this, you should get the 1, 2, 3. But now when you look at this, it looks like, you know, what we had in our reduction formulas, because like 180 minus theta, you know, this is a small angle here. So this means now I'll say my sign in the second quadrant is positive. So I'm going to have a positive of sign of 57 degrees Celsius there. Not Celsius, but 57 degrees. Now the other thing, or the other way in which you can do this, is that you can say this can also be defined as a sign of, in this case we will say 90 degrees plus, right? So now this means I have to say 1, 2, 3 minus 1, 2, 3 minus the 90. That should give me a 33. So that means here I'm going to have a 33 degrees, right? And because sign is positive, this will be a positive sign. No, not the sign here. Remember now, sign is positive, so this will be a positive. But when I use 90 plus 33 degrees, 90 plus theta, as we did it there, it has to change to its core function, right? And the core function of sine is a cos. So this will be a cos of 33 degrees, right? And that's how you find that. Again, if you press all these numbers on a calculator, they should give you the same number because they're really the same. Reduction formulas are useful in us solving big problems because, sometimes when you are able to reduce a big angle like this to a small angle like that or like that, you are able actually to solve or simplify problems, right? Now, I'll move now to 1.3, which we are given cos of 214. So now here we have 1.3, we are given a cos of 214 degrees. Now, when you want to reduce this, the first thing that you have to do, you have to look at this angle and be able to understand that this angle actually lies in the third quadrant, right? So it's in the third quadrant. And an angle in the third quadrant is defined as cos of 180 degrees. And then we are adding here. So this means here I'm going to say 214 minus 180. No. What is that? 180. 214 minus 180 degrees. That gives me a 34. So that means here I'm going to add a 34 degrees here. Now these two numbers are exactly the same because if you say 180 plus 34, you should get the 214. Now, following this, we then realize that this looks like something that we have seen, on our reduction formula diagram, where now you can then come and say, in the third quadrant, only tan is positive. So this will be a negative of cos 34 degrees. Right, it will reduce to that. Again, remember we can define this quadrant in two ways. So I can still write this as a cos of, remember I can say 270 minus some angle there. So we're going to look for that angle. If I say 270 minus 214, I get there 56. So it means here if we say 270 minus 56 degrees, we should actually get the same number that we started with here, right? So they look the same at this stage. However, going forward to this, we then have to then say, again, only tan is positive there. So this means will be a negative. Then I'm going to have it can be a cos. It can be a cos. Remember when I used 270, I have to then change it to its core function. So this means it will be a sine of 56 degrees. Remember when you use 270 minus, the name changes to the core function. Just to refresh on that. And again, if you press all this on the calculator, they should give you the same number. Now let us look at quickly 1.4, or maybe let me leave 1.4 to be done by you as a practice. I'll leave 1.4, the tan of 347, right? Try to do that and see what you get. Pointers, you first start by looking at this angle to say this angle is in the third quadrant. And in the third quadrant, we define angles in two ways. We say 360 degrees minus theta. So you then determine that angle theta. Then you'll be able to solve it. Another way in which you can define angles in the fourth quadrant would be that you say 270 plus theta. Then you determine that angle theta in that case. Then you'll be able to find your reduced angle. But you have to be careful when you use the 270 plus theta, because now you have to then write it as its core function. It has to change to its core function, right? Now let us look at question 2. Now if we look at question 2, is a question that requires us to have the understanding or the basics of, where trigonometry really starts, where we have to define those trigonometric functions. It really takes us back to how and where we define the trigonometric functions. Now, this one will require you to know the cast diagram. And in fact, if you look at this diagram also here, we still call it the cast diagram, because here we're saying only cos is positive here. All of the trig ratios are positive here. And we're saying here only sine is positive. And we're also saying here only tangent is positive. So this diagram is then, called cast diagram. If you go to the direction, can you see that we have the letters here, CAST. Some people like to call it X diagram, but this is when you measure negative angles and you actually go in the opposite direction, the anti-clockwise, right? You'll have ACTRS, and then it becomes X diagram. So usually this one is used when we measure negative angles, and this one will be used when we measure positive angles. But either way, now also to then answer these questions, we need to remember that cast diagram, and also have the basics of knowing our definition for the trig ratios. Now let's say we then look at question 2, and we are on 2.1. Now 2.1, they say cos theta is equals to 4 over 5, right? We are given here that cos theta is equals to 4 over 5. And they also tell us that our theta lies between 0 and 90. And actually, 0 and 90 are also possible values of theta, because they are equal there. Now, they then say to us, determine the value of each of the following. So with this given information, they want us to solve these ones. Now let us look at this situation very carefully before we can solve those problems. The first thing that I will say here is that we are told that theta is in the first quadrant, right? So theta is in Q1. It is in the first quadrant, because angles that range from 0 to 90 are angles in the first quadrant. Very important to see that. And we are also given this. Now what I'm going to do here is that normally you would have to draw this on your cast diagram, right? As we were talking about it here. You have to then construct this on a cast diagram. And what we do here, remember we are saying here we're having 0 to 90 degrees, right? And we are saying that our angle lies between 0 and 90 degrees, we are told them. Now with this type of a problem is that you draw a terminal ray, right? This is just a line from the origin to that part that measures an angle theta here, right? So it measures this angle theta here from, so it's any angle between 0 and 90. That's the first thing that you have to do. Now the second thing is that you then draw a triangle. You make this to be a triangle. You make this to be a triangle, right? So my line is not straight there. Just want to try to put it straight. So you make this to be a right angle triangle, not just any triangle also. In other words, we make it so that here we measure 90 degrees. It becomes a right angled triangle. Now, when you have such a triangle, you then use your definitions of the trig ratios. Remember, there is this mnemonic that people like to use that says so ka toa. So what that means is that if you have a sine, it's always defined by opposite over hypotenuse. If you have a cos, is adjacent over hypotenuse. If you have a tangent or a tan, it's always opposite over adjacent. Now, where am I going with this? I'm going to the fact that we are given a cos of theta. So this means it will be given by adjacent over hypotenuse, right? The side adjacent the angle over the hypotenuse. Now, if you look at this diagram, the angle is sitting here. The side adjacent the angle is this one here, is the side next to the angle. So it means this side here, this side here. Remember that this is our x-axis, this is our y-axis. So it means this side here would be x, and then the hypotenuse here would be r, you know. It will be given by r, because remember this thing is like a radius. If this thing were to rotate like that, it will make a circle. So this is a radius, so we call it r. Now it means this here would be my r. So it means here I'm having a 5, and here I'm having a 4, because now cos is adjacent over hypotenuse. Now you would see that, so this is x here. You'll see that we are missing y on this side, right? And to get y, you can see that this is a right angle triangle. It means we can use Pythagoras. We can say r squared is equals to x squared plus y squared, and we're looking for y. Now here we have a 5, we have a 4, so this is squared. Then we have a y squared. Then if you press this on your calculator, you should have plus or minus. So this would simplify into what? The square root of 5 squared plus 4 squared. So this is not a plus, it's going to be a negative here. We are going to have a negative here, so that we have plus or minus 3. Remember, I'm going to take this 4 to this side. So it's going to be 5 squared minus 4 squared is equals to y squared. Then we put the root sign on both sides. So I'm going to have the 5 squared minus 4 squared. So it's a minus there. Then that's how I get to the 3. So it means if you look at our numbers here of y, we have two options, positive and negative. But when you look at this side here, our y should be positive, right? So it means we're going to have a positive 3. Now, when you have done this, you can now answer these two questions that we have here. So the first one requires us to find the sine of theta. So we are given 2.1.1. We want to find the sine of theta. Now, for you to be able to find the sine of theta, you then have to use this again to say the side opposite the angle over the hypotenuse. So this will be given by 3 over 5. That's how you solve that. Then the next question, we are given the tan of theta. We are given the tan of theta. So this means if you want to solve this, you will then say tan is opposite over adjacent, meaning the side opposite the angle over the adjacent side. So that will be 3 over 4. So that will simplify to a 3 over 4. I hope you are following and it makes sense, right? Now let us try another question, 2.2. So we go to question 2.2, and then in 2.2 we are given that 5 sine beta is equals to 4. So we have 5 sine of beta being equal to 4. And we are told here that beta is an acute angle, right? We are told that beta is an acute angle. To say that beta is an acute angle, it means that beta lies between 0 and 90 degrees, right? So it is in the first quadrant. Now, before you can do anything here, you will need to simplify this so that it stays as a ratio, right? So we need to divide both sides by a 5 so that I have a 4 over 5. So I'm just dividing by a 5 here. It cancels and I have sine beta is equal to that. The reason I'm doing that is because I can draw this on my diagram, right? Because now if we draw the diagram here, we are told that this is between 0 and 90, so our terminal ray will be in this direction, right? And so if I close this to be a triangle here, right, my angle here would be the beta. And sine is opposite over hypotenuse. It means it's going to be 4 over 5 here, right? Because it's opposite over hypotenuse. Remember, you must remember your SOHCAHTOA, opposite over hypotenuse. That's how we define the sine. Now, that means we are only left now with the x part here. So I'm going to say r squared is equals to x squared plus y squared. We have here to be 5. And we're looking for x. And we have this one to be a 4. If you have been following, you'll see that you'll get the same answer as the previous one here. Our x will be plus or minus a 3. And if you look at this side here, the values of x this side, they're actually positive, right? Because remember, this is the x-axis. So this is to say here we're going to have a 3. Then now we can solve problems. The first problem that we're required to solve, the 2.2, they've given us a sine beta over cos beta. So here we have 2.2.1. We have the sine of beta divided by the cos of beta. Now, if I look at this, this is an identity. It's a quotient identity of tan. So I can write this as a tan beta, right? Remember, sine over cos is a tan. Then at this stage, I can then look at my diagram to say tan is given by opposite over adjacent, right? Opposite over adjacent. So this will be a 4 over 3. Now, if you look at the second one is cos over sine. We are given cos beta over sine beta. Now, if you look at these two, they are reciprocals of each other. So, you know, already without even doing a lot of work, I can tell you that my answer should be a 3 over 4. They should be reciprocals. They should swap as well, you know. This goes down, up. But we can do it here. If you look at the cos here, it will be given by what? Cos will be given by adjacent over hypotenuse. So that is a 3 over 5. And we're dividing this by the sine, which is opposite over hypotenuse. That is a 4 over a 5. And if we solve this type of a fraction, it will be 5 over a 4. Now, the 5 and the 5 would cancel and we get a 3 over 4. And this answer makes sense because these two are reciprocals of each other. And in fact, this is, you know, an identity, one of the identities that we have to say tan, you know, is given by sine over cos, but cot is actually given by cos over sine. The reciprocals of each other. So this is like a cot, what we have here. Now, if we go to the next question, we are given here that sine squared beta plus cos squared beta. Right, we need to simplify that. So we're having here 2.2.3. We are given sine squared beta plus cos squared beta. Now, to solve this, we are going to then define our sine, which is given by 4 over 5. 4 over 5 all squared plus the cos, which is 3 over 5 all squared, just to confirm, is 3 over 5 because it's adjacent over hypotenuse. Now, when one solves this, you'll get that this is a 16, this is a 25, you know, because you're squaring this and this. And here you will have a 9, you will have a 25. And if you look at your LCM as a 25, then I'm just going to add the 2, you get the 25 as well, right? Because 16 plus 9 is a 25. And this reduces down to 1. Now, if you already know, we have seen, this is actually an identity. You know, we have that identity that says sine of theta squared plus cos of theta squared is equals to 1. So, this confirms this identity. It's like it's a proof for this identity to say, when we have a sine squared beta plus cos squared beta, it should equal 1. I'm going to skip 2.3 for you to practice using the same methods that we used and see what you get. I think I'm interested really in 2.4. Maybe if I could look at 2.4, that would be interesting to do. If we go to 2.4, we are given that sine alpha is equals to 12 over 13, right? So we have here sine of alpha being equals to 12 over 13. And we are told here that tan of alpha is negative. So here we are told that the tan of alpha is negative. So remember when we say numbers are less than a 0, it means they are negative, right? And they then say to us, deduce cos 2 alpha plus tan alpha. Right, before we can even look at deducing that, we need to make sense out of this and draw that, right, on our diagram. Now, the first thing that I'm going to do is that I'm going to draw my cast diagram here, where I have my 4 quadrants. Remember, this is X, and this is Y. And we are saying here that we're looking at a quadrant where tangent is actually negative. Well, we know that the tangent is actually negative in the second quadrant and also negative in the fourth quadrant. So it means my terminal ray should be drawn somewhere here and here. But how do I know which quadrant it should be drawn? Well, I can firstly start looking at my sign here. We can see that our sign is positive here. Do you see that we're getting a trig ratio that's positive here? And sine is positive on this side. So it means where the tangent is negative is this side, and also where the sine is positive is this side. So sine is positive this side. So it means my terminal ray has to be drawn in this direction here. And my angle is measured here. So this will be my angle. Okay, alpha in this case. We're dealing with an angle alpha there. Now my triangle will then be completed. Maybe this side. I can draw it this side if I want to, if I like. And then here it makes an angle of 90 degrees. Now, sine is opposite over hypotenuse, right? So this means that the opposite side will be the 12 here, and then the hypotenuse will be the 13. Now, for us to get this side here, we're always going to use this here, Pythagoras theorem. And we're saying here we're having a 13, and we're looking for x here, right? And we have the y to be a 12. This means that our x will be equals to plus or minus. Now, if you solve this, I'm just going to use a calculator to save time there. We are going to have a 13 squared minus a 12 squared. That should give us a 5. So we're going to have a plus or minus 5. But if you look at this side here, or this quadrant here, you would see that my x is negative. So it means I have to take the negative 5 when I plot this. So this side will be a negative 5 there. Now, after doing that, we are now ready to solve the problem because we actually have broken down all the information that we have. Our problem was given as cos 2 alpha plus tan alpha. We have to deduce cos 2 alpha plus tan alpha, right? Now, to solve this type of a problem then requires you to know the double angle formulae for a cos, because this is a double angle formulae, right? Now, the double angle formulae for cos will be defined by what? We have 3 different types of those, and I think any one of them, if you use any one of them, you should get the correct answer. The only tricky thing with them is that some will be more longer than the others, right? You'll find that it's easier to work with other ones than others. But I think here, if you maybe take the one that says 1 minus 2 sine squared theta, well, sine squared alpha in this case, plus the tan of alpha. just for me to write these identities for you. So if you have a cos of 2 theta, it can be broken down into 3, right? It is the same really as having cos squared theta minus sine squared theta, and it is the same also as having 1 minus 2 sine squared theta. So I see here I have to put a 2, or you can say 2 cos squared theta minus 1. That's another one in which, or another way in which we can define this. So I was saying here, if you choose any one of these, they'll give you the same answer. So I just chose this one. I think it will be easier to work with it. Also, it will be easier to work with this one. You can try that one as well and see how it goes. Now here we're going to have 1 and we're going to have minus 2. Now sine is defined as 12 over 13, and this is squared here. And we're going to have a plus, and then the tan will be defined as opposite over adjacent. So this will be a 12 minus divided by minus 5, right? Because I'm saying opposite over adjacent, that is our tan. And I think at this stage, really you can press your calculator to get the value of this. Here we're going to have a 2, 1, 4, 4. 13 should give me 169, and I'm going to have here a 12 over 5. So this one here would be a negative 5, because you know the negative and the positive there will give me a negative. And perhaps if we put this on a calculator, we can quickly just get the answer. 1 minus 2 times 144 over 169, and we are subtracting here 12 over 13, and I'm getting here, okay, I see I'm getting a wrong answer here. This should be a 5 here. So we're getting an answer of negative 2623 all over 845. You can leave your answer here, or you can write it as a mixed fraction, you know, because we know that this goes 3 times. You can see there it's a 3, so it's going to be negative 3, and we can say 845 times 3, and then we subtract there 269. No, what did I do? I'm saying here 845 times 3. It gives me 2, and then I'm subtracting from it 2623. That gives me an 88. It means here my numerator will be 88 over the 45. Right, that's another way in which you can write it as a mixed fraction. You can use your calculator to do it, or to convert it to a mixed fraction. That also works. So that will be your answer. Maybe I can also do, so I'll do question, let's see, I just want to skip some of them here and leave some for you to practice. I think we have done plenty actually for these ones, and you can see the pattern. So I'll leave the remaining for you to practice. I will share with you these questions after the session, so that you can have them for practice purposes. Then we'll jump straight to question 3, really. So we'll just jump straight to question 3. And then in question 3 here, we have questions where we are required to simplify, right? So they say simplify or evaluate the following. Now, let's look at this. So now here we are on 3.1, and we are given tan squared theta times cos squared theta, right? So we have here a tan squared theta times a cos squared theta. And to do this one, I think it's a very straightforward. I'm going to use my identity for tan, which says tan can be written as sine squared theta over cos squared theta, and we're multiplying here by a cos squared theta. Now, if you look at this, 2 would cancel because remember, them being multiplied, the dot means multiplication, right? And we are only going to be left with sine squared theta. I believe this could be your final answer. And if we look at the second one, we are given 1 minus cos squared theta, right? Our identity here, the sine squared theta plus cos squared theta is equals to 1, can be broken down into sine squared theta is equals to 1 minus cos squared theta. So what I'm saying is that if I take this to this side, I can write this in that form. Another way in which I can write this is to say cos squared theta is equals to 1 minus sine squared theta. So this is when I take this to this side. Alright, I'm going to have 1 minus sine squared theta. Now, all these three, we can use them as an identity. I'm just saying this because I'm looking at this question here. It says we are having 3.2. We are given 1 minus cos squared theta. Well, it's not the theta there, it's an alpha. If I could change that to an alpha, really. So squared alpha here. So this will simply be equals to sine squared alpha, right? Sine squared alpha. Because we are saying sine squared alpha is the same as 1 minus cos squared theta. You can use it directly as an identity. And then if we go to question 3.3, maybe we can do that one as well. So we are on 3.3 and we are really given 1 minus cos squared theta all over 1 minus sine squared theta. Now, based on what I've been saying from the previous question here, I can clearly see that I have those identities. So this can be written as sine squared theta, and this one at the bottom can be written as cos squared theta. Right? And we can see that this is a tan squared theta. This is a tan squared theta because I'm having a sine over a cos there. Right? And can we have a look as well at question 3.4? I'll write it here. 3.4, we are given 1 minus sine squared alpha minus cos squared alpha. Now, to do this question, what I'm going to do is that I'm going to look at this guy here and actually change him to a cos squared theta, cos squared alpha, and then I'm still having also cos squared alpha, you see. So I'm having, this is a cos squared alpha, and I'm also having a cos squared alpha. So this will reduce down to a 0 because, we're saying cos squared alpha minus cos squared alpha. It should really indeed give you a 0. Now, if we go to the next question, 3.5, I'll quickly look at 3.5 as well. We are given here cos and sine of 15 and they're both squared. So we're having a cos and a sine. Is that a positive there? Yes. Positive sine all squared. Now, for me, when I look at this, it reminds me of algebra, right? Where we're having x plus y all squared. How you expand this? You will firstly start by squaring x. So I'm going to have x squared. Then you'll say 2 times x times y, so that you have a plus 2xy, and then you're going to square the y there, so that you have plus y squared, right? We do the same here. So we'll firstly start by squaring the cos of 15, so that I'm going to have cos squared 15 degrees. Then I'm going to take the 2 times cos times sine of 15 degrees. So this means I'm going to have a 2 sine 15 degrees times cos 15 degrees. Then I'm going to square the sine there. Then I'm going to have a sine squared 15 degrees there. Now, can we do some further simplification here? Yeah, of course we can. If we group our terms, I see an identity here in the middle. I see an identity here in the middle, but also these two, they become an identity. You see, if I take the sine squared 15 degrees and bring it here, and keep my cos squared 15 degrees here, you see, I'm taking the sine, I'm putting it here, I'm just moving it. I'm grouping my terms, if you like. Then the 15, I'm just putting it the way it is here. And here, I can change this to the identity so that it becomes the sine of 2 times 15, right? So this becomes the sine of 2 times 15. Because remember our identity for sine. Remember we have an identity that says that sine of 2 theta is the same as 2 sine theta cos of theta, right? And we are actually starting here. We are having this here. It means when I take it back, there's going to be twice this angle here. That's why I'm multiplying the 15 by the 2 there. Now, going further, we are going to have 1 here. And this one is going to give me plus the sine of 30 degrees, right? And, we all know that sine 30 degrees is a special angle. We normally draw this using a triangle here, which has the following properties. It has 60 degrees at the bottom, 30 degrees at the bottom. The length here is 2, and the length here is 3 degrees, is root 3, and here is 1. And obviously we know that sine is opposite over hypotenuse. So I'm starting here with an angle of 30. I'm going to have opposite over the hypotenuse. So this is going to give me a 1 over 2 there, right? Because opposite is 1, hypotenuse is 2, 1 over 2. And my final answer really should be a 3 over 2. It's a very simple fraction to solve that one, right? Yeah, I think that was a fun question. It was a bit involved. I'm not going to do 3.6. Also 3.7. Okay, maybe I can try 3.7. Let's look at 3.7. I think it'd be interesting to look at 3.7 because it could be a bit tricky, but yet so easy. So 3.7, we are given cos squared 15 and minus sine squared 15. So we are having a cos squared 15 minus the sine squared 15 here. When I look at this question, for me, what comes to mind is the identity that cos 2 theta is the same as cos squared theta minus sine squared theta. This is the identity that comes to my mind. And I'm having here cos squared theta, sine squared theta. It means I can rewrite this as a cos of 2 times the 15. I'm taking it back to this identity, It has to be double the angle when it goes back. Now, this would then mean that I'm going to have a cos of 30 degrees. And when we go back to our diagram here of special angles, I'm starting here on angle 30, and cos is adjacent over hypotenuse, right? Remember SOHCAHTOA, right? Always remember that in mind. So this would mean I'm going to have a root 3 over 2. Root 3 over 2, right? Let's see which one we can pick as well here. Let's see, 3.8, I'm going to leave that for you to do. I think it's an interesting one for you to do. And okay, 3.9. Let me just do 3.9 for purposes of if one is struggling. Again, it's an easy one to do. It will be fun for you to do, I think. But I think I'm interested in doing this one as well. 2 cos squared 22.5 minus 1, right? 22.5 minus 1. Again, if you know your identities, you should be able to see that cos 2 theta is the same actually as 2 cos squared theta minus 1, right? You should be able to know that identity. And again, remember, if you don't know these identities at the top of your head, you can always go to the formula sheet and look at them. The only disadvantage with that is that some of the identities are not there. In your grade 12 information sheet, they only show you the compound angle formulae, the double angle formulae, but they won't show you, square identities. They won't show you the quotient identities, reciprocal identities. They won't show you those because those were done in grade 10 and 11. So you may want to do that. And also, again, after this session, I will share with you the study guide that I've created, and you can have a revision on that, on those identities and all that. I'll outline all of those together with these questions as well. Now, if we look at this question, you have to see that this thing here, they have the same, they're the same, I'm starting off with this guy here. It means I can write this as a cos of 2 times 22.5 degrees, right? 22.5 degrees. Because when it goes back, we are going to take the angle that's sitting here, you see the theta, and we multiply it by the 2, right? It goes back like that. And then now if you do the cos of this, it should give you 45 degrees. Half of 45 is 22.5. You can confirm that on your calculator. Now a 45 degrees is a special angle. We also use a triangle to perhaps define this. So we use a triangle that has the same angles here, 45 and 45. But now with this very type of triangle, we actually have the two sides to be defined as root 2 and root 2, and this one is a 2. So there's two triangles here. The other one that you can actually use, and I think this perhaps is the one that this is 1 and this is root 2 here, right? You can use either of these triangles. Now, if we use, let's say, this triangle here, remember here it's also 45 and here is 45 as well. Now remember that cos is opposite, cos is adjacent over hypotenuse, right? So this would mean I'm having 1 over root 2. I'm going to have 1 over root 2. And if you use this triangle here, it's going to give you adjacent over hypotenuse. That will give you a root 2 over 2. So, if you press your calculator, you see that these two numbers are really the same. So it doesn't matter which method you have taught in class, as long as, you remember these triangles. Because usually these questions, you have to solve them without a calculator. I know you go with a calculator in an exam, and actually you can punch your calculator, but these are the skills that you need to learn, and especially if you are aiming to do mathematics at tertiary level, because there you don't use a calculator. You may want to start learning some of those skills now. If we move along and go along in 3.10, I'm not going to do that as well. I'm going to, I think let's do 3.10. It could make one to struggle a bit. So let me have a look at that. So with 3.10, we are given here the sine of 22.5 times the cos of 22.5. Now, when you look at this type of a problem, we can see that it looks familiar. It looks like something that we have seen before. It has this property that we are dealing with, not cos, but we are dealing with sine 2 theta being equals to 2 sine theta, cos theta. The only thing with this one is that we don't have a 2 here. So we are going to force it so that it has the 2. How do we do that? We use a method that I call we do something but nothing, you know? How do I mean? So if we come here and say we multiply this by 1, right? It will be sine of 22.5, cos of 22.5. You know, multiplying by 1, you have done something, you're multiplying by 1, but multiplying by 1 will give you exactly that. It doesn't change, right? But we know that 1 can be written as a 2 over 2, right? Because, you know, 2 divided by 2 goes back to 1. I'm choosing 2 strategically because I know that there should be a 2 for me to get to this identity. Okay, so now I'm going to then have here sine of 22.5 and a cos of 22.5. Now here I'm going to then group this one together, right? So that it then becomes our identity. Do you see? So this means now I'm going to have here, we are going to have here the sine of 45. Do you see that when the 2 goes in there, we're going to have sine 2 times 22.5, and we already know that this is 45, right? So I'm just skipping steps because we've done this, you know, before, and we are dividing all this by a 2, right? We're dividing all this by a 2. But again, if you look at our sine 45, it's a special angle. We actually can go in one of our triangles. Here you can use one of your triangles there. So if we look at sine, it's opposite over hypotenuse, right? Opposite over hypotenuse. So that is like 1 over root 2. So this would then now give me a 1 over root 2 divided by the 2, right? We're still dividing by a 2 here. And we all know that when you solve fractions, this is going to be that times, remember this is like over 1, you know. 2 is the same as dividing by 1. So this will be 1 over 2. Remember our rules, when we change this to a multiplication, we invert. We do the reciprocal of that number. So it's going to be that. And our final answer should be 1 over 2 root 2. Now, you know, if you use this triangle, the answer will look different, but it will be the same number. It will still be the same thing. Feel free to also use that other triangle for you to determine that. Now, if we then come to the next question, perhaps 3.11, it'll be interesting to also do that one. I think, you know, it will help us to remember some of the important things that we need to prepare for tomorrow's exam. So here we're given cos of 15 degrees. Let's think a bit about this. How do you think we can solve this, or what can we do with this? Because normally, you know, we're doing reduction formulae where we're taking big angles and making them to be small angles. So, you know, this seems to be a bit tricky because you're like, what should I do here? I have already a small angle. Well, we can simplify this, you know, we can simplify this and get its numerical value. How can we do that? Well, we can express this angle 15, you know, as a compound angle, right? That means I can break it into 2. You know, if you take, and usually here the tip would be, think of special angles. If I take 60 and I subtract from 60 45, you know, these are 2 special angles. I get a 15, you see that? So that means I can turn this problem or this number to cos of 60 degrees minus 45 degrees. Because when I say this minus, I get a 15 there. But now when it's sitting like this, it then becomes a compound angle formula, you know, or we can think of your formulas, your 2 formulas. So because here we are having a cos of A minus cos of B. And you know how I remember this is that you guys' generation, you are the generation of Cocomelon. And when you do this one, normally you will have a cos of A and a cos of B, right? So this one here, it's like, as I'm saying, it gives you a Cocomelon, eh? So this is how you can remember it. cocoa melon, right? Cocoa melon. So this gives you a cocoa melon. You know, you guys are a generation of cocoa melon, so that's how you can remember it. Because already here we started with cos A and cos B, it means this side we must have a sine of A and a sine of B. I don't have space there, but you can see that, right? And you know, when you're dealing with a cos, when this is a positive here, when this is a negative here, it means this will change to a positive. So that's how you remember it. So cos, and if it's a negative here, it becomes a positive here, and then you then have the sine of those two angles. It is as simple as that, right? So this is what we have in here. And of course, I mean, you would come to realize that if we have a positive here, this will be a negative this side, and you still get the same thing here. So it means with this one, we are going to say cocoa melon, so 60 degrees, 45 degrees. And then it means here it's a plus. Then we're going to have a sine of 60 degrees, then the sine of 45 degrees, right? So that's how you're going to expand that. And, you know, the tactic was that we turned these two special angles. You can see now we are dealing with special angles. And, you know, if you look at cos of 60 is going to be 1 over 2. Remember, I'm using these triangles of mine here. You know, 60 is going to be, cos of 60 is going to be adjacent over hypotenuse, that is 1 over 2. And the cos of 45 is going to be adjacent over hypotenuse, that is 1 over root 2. So I'm going to multiply this by 1 over root 2. Then I'm adding here the sine of 60. Let's go back there and check. The sine of 60 is going to be opposite over hypotenuse, root 3 over the 2. Root 3 over the 2. And sine of 45, you already know that it's a 1 over root 2. They're really the same as cos, you know, if you check them on the diagram there. And from here, this becomes a simple problem where we have to just simplify our numbers or our fractions. This is going to be 1 over 2 root 2. And this one here, we're going to have plus root 3, then we're going to have 2 root 2, right? And our denominator is the same, so I'm going to just keep it as the LCM like that. I'm going to have 1 plus root 3. I think you can stop here. There's nothing much you can do at that level. You can use the other triangle as well, where you are, you know, using a special angle of 45. It also should give you the same. It also should give you the same answer. It also should give you the same answer. So now we'll move to the next question. Yeah, I think I would love to do 3.12. I would love to do 3.12 with you. 3.12. So 3.12, we are given the tan of 180 minus x, the sine of 360 minus x, the cos of 90 minus x. Then all this is divided by sine and cos. All is divided by sine of 180 plus x, cos of 90 plus x. Then we're having a tan of 180 plus x. So just to double check, tan sine 90, 180, 90 plus 90, 90 plus 90, and then 180 plus. Okay. 180 here plus 180 plus x. Right. Now, if you look at this problem, it requires us to know our reduction formulae. You know, where we started this session, we did a recap of reduction formulae, right? Now, the first thing that we do when we use our reduction formula is that we look at this angle here to say this angle here is an angle that is in the second quadrant, right? And you know, is an angle that defines the second quadrant, and we are having a tan here. Tan in the second quadrant is negative, so that's the first. I'm going to write a negative here, and this will reduce down to a negative of tan x. It will just reduce down to that of that tan there. And you know, when you deal with these problems, it's best you also put brackets here because these numbers are multiplying each other. That will help you not to end up wanting to add or subtract them. Now, the same thing here, we look at this angle here, we can see that it is an angle in the fourth quadrant because we're saying 360 minus x, you know, that is the fourth quadrant. And here we are dealing with sine, and only cos is positive in the fourth quadrant. That means this will be a negative sine of x. It will reduce down to a sine of x. Now, when we look at this one here, we're having a 90 minus theta. That is the first quadrant, right? And we are dealing with a cos here. And remember, the angle of 90 minus theta will make this cos to change to its core function. That means we will then write this as a sine now of theta. Remember, all our trig ratios in the first quadrant are positive. So this will be a positive sine of x. Then we are going to divide all this by what we have here in the bottom. So here we're having this is the third quadrant, right, where we're saying 180 plus theta. But in the third quadrant, only tangent is positive. So this will be a negative of sine x. I'm going to put brackets there. And when you look at this angle here, it's actually the second quadrant, because saying 90 plus, you should fall in the second quadrant. And we are dealing with a cos really here, right? And only sine is positive in that quadrant. So that means this would be negative, right? But you also should keep in mind that when you then say 90 plus, it then makes this to change to its core function. And the core function of cos is a sine, right? So when you have a sine here, it will change to a cos, and it will be negative because, you know, in this quadrant, only sine is positive, and I'm dealing with a cos there. And this will reduce down to an angle of x. Then I will close my bracket there. Then I have tan of 180 plus theta. 180 plus theta, we know that it is actually the third quadrant, right? And in the third quadrant, the tan is positive, right? Tan is positive, so this will just reduce to a tan of x. Now, if we move along with this, we will then get to a point where we just need to simplify this, right? This is a very interesting question because when you look at these terms, they are actually all the same here. Do you see that I'm having a sine here and a sine here and a sine here? I'm having a tan and a tan. So this for me will reduce down to something like 1. Why? Because this and this would cancel. This and this would cancel. This and this would cancel. So I'm having 1. So I'm having negative 1 times negative 1 times 1, right? Negative 1 times negative 1 gives me 1. 1 times 1 is a 1. So I actually have 1 there at the top. Now at the bottom here, I'm actually having, what do we have here? We have negative 1. We have negative 1. We also have 1, right? Remember when they cancel here, I'm going to have negative 1 times negative 1 is a 1. 1 times 1 again is a 1. Then that means I'm having a 1 here at the bottom as well. Then 1 divided by 1 is just a 1. So this becomes as simple as that. Very interesting question. Let's see. I think we can also do 3.13 together. Yeah, maybe we can break that together as well. So we are given here 2 sine 90 minus theta plus cos 90 plus theta, right? So we are on 3.13. And then we said we're given sine of 90 degrees minus theta plus cos of 180 minus, this was a minus theta. This is a minus theta, yes, the minus theta divided by sine 90 minus theta minus cos 180 minus theta, okay? So that is sine 90 minus theta cos of 180 degrees minus theta. So again, this one will require us to use the knowledge of reduction formulae as well. So if we look at this here, we know that that is the first quadrant, and this will change to its cofunction, right? Because when we're having 90 minus, this has to change to its cofunction. So this is going to be positive cos, because the cofunction of sine is a cos, right? And we're going to have it to reduce to a cos of theta. Then I'm going to add here, let's see, I'm going to add here, if we look at this angle here, it is in the second quadrant. And in the second quadrant, only sine is positive. So that means I'm going to have a negative. That's the first thing. And this will reduce down to just the cos of theta. You know, because when it's like this, you just reduce it to a cos of theta. The angle reduces to a cos of theta. Now, when we go down here, I think I need to close my brackets. If we look at this angle here, it is in the first quadrant, and so it means it's just going to, no, not the sine, it will be its cofunction, cos of theta. It will change to a cos of theta. So this will change to a cos of theta. I mean, these are the same, is what we did there at the top. And then if you look at this angle here, is the second quadrant. They look to be the same, these questions. Let's see. Okay, the only difference here I think is that we have a negative here. So this would be the second quadrant, and in the second quadrant sine is positive, so this will be negative cos theta, right? This will be negative cos theta. Can we simplify this? Yeah, we can. I think the first thing maybe is to really remove the negatives there, so that I have a negative cos theta. This will give me a negative cos theta. Remember, this negative and positive will give me negative. And then this will divide by cos of theta plus cos of theta, right? And now we will say, let's see. Okay, this will be a cos of theta minus cos of theta. There's nothing much I can do here. Here I can add these two so that they give me 2 cos theta, because I have 2 of them, you know. It's like having x plus x, it will give you 2x, right? Think of it that way. We're adding the same trig ratios. Now it tells me that I should take out the common factor, because I can see that they'll cancel here. You see here we have a common factor of cos. So that now I can take out, no, not 2, but the cos of theta. It means here I'm going to remain with a 2, and here I'm going to remain with a 1. Remember, if you say this times this, it will give you 2 cos theta. And if you say this times this, it will just give you negative cos theta. That's why I'm taking out the common factor. And I can see here I'm having cos of that. The reason I'm taking common factor is that I saw that these 2 would cancel each other. Yeah, I can sort of see them when I'm observing this problem. Then here we're going to have a 1. At the top here we're going to have a 1, because, you know, 2 minus 1 is that. And I'm having a 2 there at the bottom. So this reduces to a half, right? Um, right, I think we have pushed a bit. We are now at 3.14. I'm not going to do that. I think I'll leave that for you also to practice and see if you can get it. And we'll move to question 4, which is really our last question for this session. So question 4 will be looking at proving identities. I think I'll close off this chapter by just looking at general solution after doing question 4. But before we attempt question 4, perhaps we can take a quick 5 minutes break. Then we'll resume and just kill proving identities. Right. Let us continue with question 4. Yeah, I hope you had a bit of some break there because we've been pushing for some time now. Now, when we look at question 4, we are given or we're required to prove identities. You know, an all-time favorite question, you'll always get it in the exam, right? So now let us go through that one. Question 4, we're starting off with 4.1. We are given here tan squared theta minus sine squared theta, when we are saying this is equals to the product of the square of tan theta and sine squared theta. Now, when we deal with proof of identities, we actually have the left hand side and the right hand side. We actually required to prove that these two sides are indeed equal, right, or the same. So normally the tip here would be take the side that is most complicated, because then it gives you an opportunity to simplify it. And you know, when you simplify, it will then go to the other side that you're trying to make it to be equal to. The thing with proof identities is that sometimes you then also have to look at the other side as you are solving, because you want them to be the same, right? You want them to be the same. But this problem really is not different from the previous questions we were doing in question 3 of simplifying, because really, if you come here and say the complicated side is this side for me, you know, I'll take that one, meaning I'm going to come here and say I'm taking the left hand side. That means I'll take the tan squared theta minus the sine squared of theta. Then I have to simplify this. That's what I'm saying. When you're at this stage, you realize that these questions are not different from the questions that we were doing in the previous question 3 of simplifying, because we really want to simplify this. But the thing is that the only different thing is that when we simplify, we have to make sure that it goes to that direction. So let us go through it and see. So naturally, what I will do here is that I will turn my tan theta into its identity, the quotient identity, that says tan theta squared is the same as cos theta squared, right? And I'm going to leave this sine squared theta as it is for now. And at this stage, I think when I'm looking at this problem, it becomes fractions, you know. This can be seen here as 1. Right? So that when we solve this, I'll then say my LCM here is actually a cos squared theta. And what I'm going to do here is that I'm going to say cos squared theta divided by cos squared theta, it will give me 1. Then I'll say 1 times that, right? 1 times sine squared theta, I'm going to get a sine squared theta. So it means here we're going to write sine squared theta. Let's recap that. Let's go through that again. We are saying the denominator divided by the denominator. So I'm having here a cos squared theta divided by a cos squared theta. Then I get a 1. Now I take this 1, you know, 1, I multiply it by this number here. So I multiply it by sine squared theta. It then gives me the sine squared theta. I put it there. Now let's do the same thing now with this one. I'm saying 1 divided by this, right? So we're saying cos squared theta divided by 1. It gives me a cos squared theta. Then I take the cos squared theta, multiply it with the sine squared theta, right? Then I'm going to have a minus. Here we're going to have minus sine squared theta times the cos squared theta. We're going to have the product of the two. Now, when you look at this problem, it says to me that, you know, there's a common factor of sine there. I see a common factor of sine, yeah? So I can take that out, I suppose. I'm not too sure where I'm going with it. But I think, yeah, I mean, there's nothing much you can do here except taking out a common factor. I wouldn't advise changing this to the identities, the 1 minus cos squared or something like that. I'll say try to simplify it by taking now here the common factor. Here I'm going to have a 1. I'm going to have minus cos squared theta. Because if you multiply this, you get that. If you multiply that, you get that. So I'm still having here at the bottom the cos squared theta. But if you look at this, or in fact what I can do is that I can change this to its identity, because I can see now they cancel out. Nope. So what I wanted to do here, I wanted to change this to a 1 minus sine squared theta. It's not going to help me. So I think I'll leave this as it is now. I can see that this one here will actually give me a sine squared theta. And I have a sine squared theta here, right? And this one here will be a tangent, right? Can you see that? So here we're going to have sine squared theta times the sine squared theta all over the cos squared theta. But I'm saying if I group these two here, they give me a tangent. So these ones will give me a tan squared theta, sine squared theta. And when you look at that, it's exactly the same as the right hand side. We'll then say this is equals to the right hand side. Hence proved, right? This is proved. Hence proved. Let us go to the next one. We are given here in 4.2 1 minus sine squared theta times 1 plus tan squared theta is equals to 1, right? Right, as I said, the tip here again will be what? We take the side that is more complicated so that we can simplify it. So if you look at these two sides here, I'm having a 1 on the right hand side, I'm having this long thing on the right hand side. I mean, if you try to take this and want to take it back here, it's going to be extremely difficult, because it's possible, but it's going to be extremely difficult because this is already simplified. 1 is just one single number. So we'll take the left hand side where we say 1 minus sine squared theta, and we're having here 1 plus tan squared theta. And when we simplify this, this for me is a binomial, it's a binomial by a binomial. It's the product of binomials, two binomials. So this means I'm going to say 1 times 1, and I'm going to use the FOIL method. It's going to give me a 1. And then we are going to say 1 times tan squared theta. So this means here I'm going to have a plus tan squared theta. And we then going to say this times that is going to give me a negative sine squared theta. Yeah, I think if I do it that way, it's going to be too long. Expanding this will be too long. I think I wouldn't take that route. You can get the answer by doing that, but it's going to be too long. I think what we can do here is that we can change this to our identity of cos squared theta. We can say this is the same as cos squared theta. And then we are going to then leave this as it is for now, right? Yeah, and at this stage, I think that's where we can actually multiply this inside here, to avoid it being like that too long. So this would mean I'm going to have here my cos squared theta, and here I'm going to have plus cos squared theta, but I'm going to change this guy into a sine squared theta over cos squared theta, so that now the cos and the cos cancel each other out, and I'm going to have cos squared theta plus sine squared theta, and this is equals to 1. We know this identity, right? And then we can therefore say the right hand side is the same as the left hand side. Right, that's proved. That's proved. So we've proved that that side is equals to 1 as well. Let's see. The next question would be question 4.3. I think I'll leave 4.3 for you to try, and I'll do 4.4. Right, so 4.4 we are given cos to the power 4x. No, we are given a sine actually. So we are having a sine here. So we have here sine to the power 4x. So sine x to the power 4, that's how we would sort of say it. Cos x to the power 4. And we are saying this is equals to what? We are saying this is equals to cos 2x. Cos 2x. So this is the same as cos 2x. Okay. Now, I think for me here, the left-hand side is much more attractive for me. I'll take that and try to simplify that. Now, when you look at this thing, it reminds me more of the difference of two squares, all right? So this reminds me of the difference of two squares. So if you were to have x to the power 4 minus y to the power 4, this will be written as x squared minus y squared, x squared plus y squared. So we're going to do the same thing, because this, remember, it's like x to the power 4, y to the power 4. So this means I'm going to have my two brackets such that I'm having here a sine squared x minus cos squared x, and here I'm having a sine squared x plus cos squared x as well. Right? Maybe if I could erase here, since we have established that, and maybe expand these ones properly. So here we are going to have a sine squared x plus a cos squared x. Now, when you simplify this, you would see that this here gives me a 1. It's an identity, right? And this actually is just the double angle formula, right? Let's see. Yes, this is a double angle formula. So that means here we're going to have a cos 2x. And here we're going to have times 1. And eventually you just have 2 cos x. And then, this is the same as the right-hand side. Right, hence proved. Right, hence proved. So that is proved then. We'll move along to the next question, which is question 4.5. I think that what I'll skip for you to have some practice. And perhaps I'll do question 4.6. So here we are having sine over cos. Right, let's see. Right, these two sides, they look fairly the same for me. I think any side that you take here would really give you the same answer. Maybe I can take the right hand side for a change, right? And we're having a sine theta over 1 plus cos of theta. Now, if you look at this identity, you'd see that how we can tackle this is that we can use that method where we're saying we're doing something but nothing. So that means I multiply here by a 1. When you multiply this by a 1, you are not really changing this, it's still the same. So that then now I can write this as sine theta over 1 plus cos theta, and I'm multiplying here now. So I'm going to multiply this by my denominator, where I'm going to say 1 plus cos theta over 1 plus cos theta. Remember, these two, they cancel out, they give me 1, and I didn't do anything. This still looks the same as it was, right? Now, at this stage, we then can now multiply our terms that we have created to say this multiplied by that, and that multiplied by that. So this means here I'm going to have a sine of theta, and then here I'm going to have plus sine theta cos theta, right? And at the bottom here, we are going to have okay, so I think I did my multiplication a bit in a wrong direction here. So what we should multiply this with is that I should remember, I want this to go back to this side, right? So I should multiply by the numerator here, right? I should multiply here by 1 minus cos theta over 1 minus cos theta. This gives me 1, and 1 times that, it's still that, it didn't change. Now here I'm going to have a sine of theta, then I'm going to have minus sine theta cos theta, because I'm multiplying this by 1 and multiplying that together. So sine theta times 1 is just sine theta, and sine theta times cos theta, it gives you sine theta cos theta. Now here at the bottom, we then have a difference of 2 squares. Do you see that this is a difference of 2 squares? So we we can or maybe at this stage I can write them as they are. Okay, let's do this. So here I think I can just say sine theta 1 minus cos theta, right? And this one is a difference of 2 squares, so this would mean I'm going to have a 1 minus cos squared theta. This is a difference of 2 squares. A difference of 2 squares, you would have x squared minus y squared. It simply gives you x minus y, x plus y. So if you check here, I'm starting off with this is positive, this is negative. So it will just go back to a square of 1 is 1, a square of that is that. So I'm just taking it back in that sense. And yeah, at this stage, I think, remember, we're trying to go back to, okay, So you can see here we're having a square. Remember that we said in trigonometry, when you have sine squared theta, it is the same as sine theta squared, you know. If you were to have cos squared theta, it is the same as the square of theta. So the same thing here will apply. We'll say here we have a sine theta 1 minus cos theta all over. Now here I'm you know, this would be the same as having no, let's see. No. This question is going to a different direction now. Can I perhaps take, yeah, let's take the left hand side. Let's try the left hand side and see how it goes. Let's see. I'm getting lost a bit here. Maybe I'm getting tired. It's been a long session. Let's see. We are on the left hand side. Let me take the left hand side. I'm having 1 minus cos theta all over sine of theta. Now, here I'm going to multiply by 1, right? Because, you know, we're using that technique where we're saying you're doing something but nothing. Because remember, when you multiply by 1, this doesn't change. Now that I've done that, I would then turn my 1 to something so that I have sine theta here. So I'll turn my 1 to 1 plus cos theta over 1 plus cos theta. Remember, these two, they just cancel each other and give me 1. So, you know, I've done something but nothing, right? To that end, I think now what I will do here from this point on is that I will multiply these two out. They give me a difference of 2 squares. So this goes back to what we were doing in the previous one. Let's see. So this will be a difference of 2 squares. But here at the bottom, I'm actually going to have sine theta 1 plus cos of theta, right? And we know that this is the same as sine squared theta, right? So that now I have sine theta 1 plus cos theta. And if you look at this one would cancel and I'll be left with 1. So remember here I have 2 of cos theta, so sine thetas I mean. So the sine theta here would cancel and I'm going to be left with 1 there. And this is proved actually because now I have the sine theta alone, which is that all over there 1 plus cos theta, and this is equal to the right hand side. So it is proved. I wonder what happened on the other side, but I believe you can get it. I'm not sure what mistake I was doing there, but if you have a look at it, I believe you can break it down and be able to do it. The other problem that I'm interested in doing, perhaps, I think that will be the last one, and then I'll stop. I'll leave the other ones for you to do. The last question that I'll do, I think it will be let me see, between 4.7, 4.8, 4.9. Which one can I do there? Let's see. Okay, maybe let's do all of them. You know, maybe let's do all of them. Let's look at 4.7. We are given sine 2x plus cos 2x plus 1. And all this is divided by sine x plus cos x. And we're saying this is equals to 2 cos x. Okay. 2 cos x. Obviously, the left-hand side is much more complicated. I'll start by doing that. So on my left-hand side, what I'm going to do is that I'm going to use my double angle identity for sine, which is going to give me 2 sine x cos x, right? And we are going to also do the double angle for this cos here. Remember, there are 3 of these, right? So I'm going to take the one that has a cos. I'm going to take the cos 1. The reason being is because I see this 1 here would become 0. It will cancel with the 1 on the cos. So it's going to be 2 cos squared x. So this is x minus 1. And I'm having a plus 1 there. So this is my identity here, but I'm having a plus 1. So the reason I've taken this specific identity is because of I want these 2 to cancel. Because you can see here we don't have 1 on this side. So I just want to eliminate that number. And this side, there isn't much that I can do for now. I'll just leave it as it is. Now these 2 will give me a 0. They will cancel each other out. And we can see here that we have a common factor of cos and a 2, right? So that means I can take the 2 out and the cos x out, so that I'm left with sine x and I'm left with a cos x here. Because if you multiply these 2, you'll get a 2 sine x cos x. Then if you multiply these 2 here, you'll get a 2 cos squared x. Now, here at the bottom, I still have sine x plus cos x. I think you can see the answer now, right? Because these 2 would cancel each other out. And indeed, I'm left with 2 cos x, which is equals to the right-hand side. Hence proved. Hence proved. Now let us go to the next one. I think I just want to do all of these 3, the last 3, because I just feel like you might struggle with them. A little bit of explanation there and there could help, or maybe sharing some of the ways in which this can be done. Now, if we look at 4.8, we are actually given 4.8 we are given 2 that, so that looks like an identity to me, yeah, of sine really. And here at the bottom we have cos 4x minus sine 4x. And we are saying this is the same as tan of 2x, yeah? Obviously, the left-hand side looks complicated to me. And as I was saying, I think this is, this part here, the top part would be sine 2x, right? Because this is an identity here. And here is a difference of 2 squares again. We have dealt with this before, where we had cos squared x minus sine squared x, and we're multiplying this with cos squared x plus sine, this is a sine here, sine squared x. You should remember this from the previous question that we did. And at this stage, if we go down here, we know that this is going to be a 1, and this is a double angle formula for a cos. So I'm going to have a sine 2x divided by cos 2x, right? And here we're multiplying by 1, right? Because this here is a 1. And you can see that this becomes an identity for tan, because remember we're saying tan theta is the same as sine theta over cos theta, right? Except here now there are double angles. but it will give you the same thing. So this will be a tan 2x, and actually this is the same as the right hand side, right? That's proved. So this is also proved, right? Now we're going to 4.9. 4.9, we are given sine 3x over sine x, yeah? This is divided by the sine of x, and we have negative cos 3x divided by cos x. Then they're saying this is equals to 2. Guys, I mean, you know, when you want to solve a problem like this, already you can see that the left-hand side, again, is the one that is much more complicated. So it would be best to take the left-hand side, because, I mean, if you take a 2, you can prove it, but it's going to be difficult for you to take 2 to come back this side. You'll have to do a lot of interesting things. You have to be really powerful with mathematics, but it's possible you can do it. But to save time and to make sure that you kill this question, it will be best to take the left-hand side. So our left-hand side is given by sine 3x all over sine x minus cos 3x all over cos x. Now here we are going to take the LCM, right? So that my LCM is the product of these two, right? Is the product of our denominators. You know, this becomes my LCM. Now with this LCM, what we do is that we say this divide by that, divide it into that. So I'm dividing here by sine x. You can see that the sine x and the sine x will cancel each other. Then I take the cos x, I multiply it with the number here at the top. So that now I'm going to have sine 3x times cos x. That number I put it here, sine 3x times cos x. Can I recap that? I know this usually sometimes gets confusing, right? My LCM is the product of these two. I then take this, I divide it here. So this means I'm going to divide here by sine x. So this would cancel. Now I'm left with cos x. I take the cos x, I multiply it with the number here at the top. So this means I'm going to have this number, sine 3x times the cos x. Then we do the same thing. We're saying this divided by that here. It will give me a sine x, you know, because these two would cancel. I'm going to have sine x. Then I'm saying sine x times cos 3x. So that means I'm going to have this negative here coming down here, and I'm going to have the cos of 3x times the sine of x. Right, then we continue. Let's look at where we are going. We need a number 2. Okay, we just want, so it means this one we have to, you know, break it down until it really it reduces down to a 2. We just have to simplify it as far as we can. Guys, you know, as I'm looking at this problem, I'm really smiling to myself, because really this here, when I look at it, for me, it says to me I am a compound angle formula, right? I'm a compound angle formula. You know, when you have a compound angle formula of a sine, you'll have a plus or minus a b, and this should give you. So when you have a sine, you actually would mix these two. You start with sine a, and then it'll become cos b. And the sine, you know, the best way to remember this is that when you have a sine, the sign doesn't change, right? When we have sine, the sign doesn't change. It means here we're also going to have plus or minus, right? So sine means the sign doesn't change. It only changes when you're dealing with a cos, cocomelon. We're talking about that, right? To say, you know, to remember the compound angle formula for cos is cocomelon. It starts with a cos, then it will take sine. But the sign will then have to change. So here it doesn't change, and then you will then have here the cos of a, then the sine of b. So here they swap around. Remember, sine took a and then cos took b. It means now they have to swap around. Cos has to take a and b has to take the b now. Now if you look at this thing here, is exactly this formula here, but now it takes the one with a negative. Yeah, so because if you check here, this is like I'm having my a, this is my b. Look at this is my b, this is my a. Can you see that? So this will actually reduce down nicely to be a sine of 3x minus x, and here I'm going to have sine x cos of x. And you can just manipulate those together there. You can just do the operation there, which will give you a 2x, right? That should give you a 2x, and we're still having here sine x cos of x. Let's see, what can we do here? Well, I mean, this also again is an identity. I see here, you know, we have something that we can do. Actually, already I see the answer, because here, remember your identity, when you have sine 2 theta is the same as 2 sine theta. Can I write this this properly here? When we have sine 2 theta is the same as 2 sine theta cos of theta. So it means I can expand this to a 2 sine of x cos of x, and then I still have here the sine x and the cos x. Now these two would cancel, right? And I'm only left with the number 2, and this is the same as the right hand side. This is the same as the right hand side, and we can then conclude to say, hence proved. We have proved our question, our identity. Guys, this was the last question here that we're doing. I think we've pushed enough for the day. I wished that I had time to do general solution with you, but I want to maybe share with you the conditions of a general solution, right? Because I always say, or when I tutor students, that if you know how to prove identities, how to simplify, then you are halfway in terms of doing general solution. The only thing then with general solution is that you just have to put the following statements, the conditions that I'm going to put here for you. I just want to put them down for you so that you know those conditions. Just a second here. Okay. So you're going to do general solutions for 3 functions, or you can say 3 trigonometric ratios, right? So the first one, so here I'm saying we are looking at general solution. Remember, when you apply or you do general solution, it's like solving trigonometric equations. And again, you do them in the same way that you do solve for x, except in this case, they are trigonometric equations, right? And that's why I'm saying that you need to have the skills of simplification, the way we're simplifying or proving identities. Now, when you are dealing with a function or a trigonometric ratio that is defined by sine, so for example, if you are dealing with sine theta, right? And you know the function of sine theta will be defined. So here I'm saying we are having sine theta is equals to a. So this is sine theta is equals to some number a, right? And our a here should be an element of -1 and 1. You know, when you do your domain on the function of a sine graph, right? It ranges from -1 and 1, right? Not domain, but the range. You know, the sine graph, the range, it moves from, you know, -1 to 1, where you look at your amplitude, really. So if you have an equation that looks like this, that's sitting like this, then when you want a general solution for this, you will take the inverse. You will take the inverse of this function. You will say the inverse, sine inverse of a, right? So you know on your calculator you can press the sine inverse. When you take the sine inverse, you'll only be left with that theta there, which is an angle. So it helps you to find the angle, right? But when you take that inverse, you actually have to add here k times 360 degrees. This is because of, we can do angles that are greater than 360. Even if when you look at your sine graph, it can go until infinity. It goes, it's a wavy function. It goes like this. It can expand and exceed 360. It can go beyond 360. So that's why here we're having a multiple of k times 360. So, we're saying here that our k should be an element of integers, right? So it can be, your integers are numbers that are both positive and negative, including 0. So it's like 0, 1, 2, 3, 4. Or you can have -1, -2. So k can be any of those numbers. Remember, we can also have negative angles. So that's how you're going to define a general solution. Now, this is to say that if maybe you were solving a problem, let's say you were solving a problem where you end up having the sine of theta is equals to, let's say, 1/2. So this means here you're going to say this is equals to the sine inverse, right? So you'll go to a calculator and say the sine inverse is going to be shift of 0.5, which is 1/2, and this will give you a 30. So you'll then have a 30 degrees. But you then have to say k plus k 360 degrees. And all the time you then have to write this condition to say k is an element of integers. We call this a general solution, because these are the solutions that the numbers that will satisfy or make this equation to be true. So our k, as we said, it will range. Remember, k will be equal to, so it will come from negative numbers. So negative, let's say 2, -1, 0, 1, 2, and it will go on like that. So if you put these numbers here, -10, -9, and so on, 0, 1, 2, you put them here, do you see that you'll have an infinite amount of theta? You'll have a lot of numbers of theta. So sometimes in the question, they'll tell you that maybe your theta should be between 0 and 180 degrees. So that would mean that you will start testing it. You will put, let's say, for example, if I put 0 here, I'll have 30. 30 falls within this interval, right? So it means theta will be equals to 30. Then we can have 1. If I put 1 here, it then means I'm going to have 30 plus 360. Do you see that 30 plus 360 doesn't fall within this interval? It is not in this interval, so it means it is not a solution. But if you try -1, if we put -1 here, then we'll have -360. That means now I'm going to have 30 minus 360. And then that gives you -330. So it's also not a solution. So the only solution that we'll have here will be, because already you can't go to a 2 and you can't go to -2, because you'll get values that are already outside of that interval. If they give you a bigger interval, let's say they give you something like 0 to 360, then you'll accommodate the other numbers that are within that interval when you test them here and you put them there. I hope that makes sense. So this is when you are dealing with sine theta or a sine graph. You also can have a situation where you are dealing with a cos graph, right? So this is when you're having cos theta being equals to a, and again, we said a should be an element of -1 to 1, because that is your range for your function. Then if this is the case, then you will have theta to be equal to plus or minus the cos inverse of a, and then you're having plus k 360 degrees here, where our k is an element of integers. This again becomes a general solution for cos, And in the same way that we used it in when we're doing sine, you can also test different values. So it depends. If the question requires you to find those specific numbers on an interval, you'll then find them. But if they say write a general solution, you'll just leave your answer at this, Then the last bit of it that you will get will be if you have the tan theta being equal to A, and they then say here we have A to be an element of real numbers. Now here our A is not restricted to -1 and 1. Why is that the case? Because if you were to remember our tan graph, right, it goes like this. It has asymptotes, 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 and then it curves like that. It curves like that. Do you see that our range here is all the real numbers, it's all the y values here that go to infinity and negative infinity like that. So it doesn't have a domain of -1. Remember, with a sine and a cos graph, you have -1 and 1. So that's why our A is restricted to A. So with this one, it becomes an element of all the real numbers. But now, if you then have a situation like this, then our general solution would be that the theta will be defined as tan inverse of A plus K 180 degrees. So very important to keep this in mind. It is not 360 anymore when we're dealing with a tan. It's 180 degrees. And this becomes your general solution. I think if you keep this in mind and you know this, it becomes easier for you to solve general solution problems. Maybe just as a practice, before we close the session, I would do maybe one problem on this, just for us to practice this and see how you apply this, right? How do you get to this? So say, for instance, they say to you that you have to solve. So I'll say this is a problem that we have here. They say to us, solve for theta, right? If you are given 2 sine theta plus 15 degrees, right? Let me write this down here. So we say solve for theta if we have 2 sine theta plus 15 degrees, and then we have here √3, and we're saying this is equals to 0. We then give you conditions to say theta should be an element of 0 to 360 degrees. Alright, so we have a condition here. Now, how do we solve this problem? Well, the first thing maybe is that we need to simplify it, right? And to make our life easy, we'll then start by saying let P be equal to theta plus 15 degrees. So I'm taking this guy here to make him to be, a single value like a P. So this means here I'm going to have a 2 sine P plus √3 being equal to 0. Then I'm going to say sine P is equals to -√3 over 2. I'm taking the √3 to this side and dividing by the 2, right? Now, after doing this, we are at a position where we actually have that condition that says we have a sine theta being equals to some number A, right? So we are here now. We are at this point. We're saying sine theta is equals to the A then. It means at this stage I can apply my general solution. I can come here and say this would mean that P is going to be the sine inverse. So we're going to take the sine inverse. It's going to be shift sine √3 over 2. and this gives me negative 60. So it means I'm going to have a negative 60 degrees plus K360. Right, we're having a K360, and we have to then put this condition to say K is an element of real numbers. Or, remember there were two conditions. The first one was that we have to take the sine inverse of 360, and then the second one, I didn't write the second condition here, no? Okay, because sine has two conditions. Yeah, I think I didn't write the second condition here for the sine graph. I'm realizing that now when I'm actually doing it for you. So the other condition here would be that we have theta to be equal to 180 degrees minus the sine inverse of A plus K 360 degrees. The reason why we say 180 minus the sine inverse is because of sine also exists in the second quadrant. It is in the first and second quadrant, right? And the same is true with these ones. The reason why we have plus or minus is because of, our cos would be positive in the first quadrant and also negative in other quadrants. So here we then have to look at the other condition that says P is equal to 180 degrees minus the sine inverse, which is going to be, minus 60, because we know that the sine inverse is 60. We just took that, and we're going to have plus K 360 degrees. And again, here you have to say K is an element of integers. Very important to write that statement. They give you a mark for writing that statement. And then you can really just punch this on a calculator to say 180 plus 60. Remember, the negatives here would be positive. So this would mean I'm going to have a 240. Was that a 240? Yes. A 240 plus K 360 degrees. Right? But we have to keep in mind that P is equal to remember we said P is equals to 15 theta plus 15, right? So it means this would mean if I take the first one there, I'm going to have if I take the first one there, I'm going to have theta plus 15 is equals to negative 60 plus K 360, right? And this would simplify to our theta being equal to what? Negative 60 plus 15, giving me negative 45. Am I doing it correctly? No, I'm not. I'm going to have a 60 minus 15. That should be 75, yeah? So we're going to have negative 75 here. Because remember, this 15 goes to that side. It becomes negative 60, negative 15. And we are adding this. We are adding K 360 degrees here. Right? And then I can just say this is equation 1. This is my first equation. And then the second equation will have theta plus 15 degrees. Remember, I'm doing this one now. I'm doing this one here. So this would be equal to 240 degrees plus K 360 degrees. Right? And this would mean that my theta would be equal to 240 minus 15, right? And that is 225. So here we're going to have 225 degrees plus K 360 degrees. Right? And we then have to find our values of theta. Right? We then have to find our values of theta. To find our values of theta, we just use a calculator. I'm going to use equation 1 and equation 2 to do that. So we're having negative 75 here plus, remember, I'll start with a 0 here. So if we start with a 0, if we put a 0, I'm putting a 0 here on the K. Remember, they said here we have to move from 0 to 360, right? So I'm saying my K is 0, is 0 here. Remember, k is your integers, right? -1, -2, -3, 0, 1, 2. So I'm starting with a 0 here. And when I put a 0 here, this whole thing disappears. I get a -75, right? Do you see that -75 doesn't fall within this interval? So it means -75 is not a solution. But if we try, let's say 1, if we put 1 here, I'm then going to have -75 plus 1 times 360. 1 times 360, that gives me 285. If you look at 285, it falls within this interval, right? So it means theta is going to be 285 degrees as my solution, right? And if we maybe put a 2, we go on to a 2 here. We put a 2 here. We get the 645. Look at this. The 645 is outside of that interval, right? 645 is out of that interval. It's not a solution. So that means already I can stop looking at the 3, 4, going forward. I can test the -1 perhaps, or going to the other side. If we test -1, look at that. We get the -335. Doesn't fall within 0 to 360. So it's not a solution. So that means I can stop. So for this part of the equation 1, we are sorted. We now focus on equation 2, right? We'll then focus on equation 2 to say the other solution that we can have here is that if we put a 0 here, we're going to have a 225. So 225 becomes a solution. 225 becomes a solution because it falls within this interval, right? And if I put a 1, let's test a 1 there. 225 plus 1 times 360. Already this will be big. I mean, you can see that already I have 225, you know. So 258 is above. And then if, let's say, we try -1 there, I get a -135. You know, -135 doesn't fall within this interval, right? We can't have an angle there. So it means our solutions is only these two numbers. Theta is allowed to be 285 and 225 within this interval. So this is how you're going to solve it if they give you an interval. If they don't give you an interval here, your answers will be left here. You'll only leave them here in equation 1 and equation 2. So the question will be specific when they ask you. They'll say, find the general solution. And then they don't give you an interval. It means you leave your answers here. Sometimes they'll say, solve for theta in this interval. So that means you have to test that interval within the numbers of k being an element of integers, right? So this means your k would be numbers that come from -3, -2, -1. So these numbers, they come from -infinity. They're going in that direction, right? So you test all of them to see if they give you those numbers. So here will be 1, 2, 3, and so on. They go to positive infinity as well. So you can have a lot of solutions depending on how big your interval is. Grade 12 learners, will stop here. I think we've pushed plenty for the day. It's been a great session. I hope it helps you for the exam tomorrow, and all the best.